There's lots of other types of ways to combine some of these ideas we've had here and give you even better classifiers. This one's fun because it's called, it's just extremely randomized trees. We say random forest, now we're going to say this one's more random. So what do you call it? Extremely randomized. Somebody later on came on with one more that is even more randomized, and she's like, well, what do I call it? I'm going to call it the totally randomized. It's like those telescopes that people create, the very large telescope array. It's like the most creative algorithm name ever. At least AdaBoost had a reason for the name. But it does help you remember what it is, right? So extremely randomized, it's not that it has more random, like the choices are more random, because in random forest, your selection of data points and features is random. Extreme randomized trees are going to do random choices at more points, right? In more times, right? So we've got still an ensemble of trees, right? So we're going to learn a bunch of trees, and the data set is going to be random, right? And so all the random things I'll circle in other colors. Right, so you pick a random sample of data points. You pick a random feature subset, right? Just like Random Forest did. But then you also have to pick, like for each of these features, right? So say for this feature point, you've got basically your values of your feature from 0 to F to max, whatever it is, right? So if it's age, it's like 0 to 100 or 109, however old people live, right? In decision trees, we try to pick like an optimal cost decision point, right? In random forests and extremely randomized trees, we just literally pick a random number out of the air in between the min and the max, and then we go there, right? That's an unreadable piece of Scratch. Right, so we randomly pick a split point and we just use that. So it seems like a bad idea because you're not even picking, like maybe you picked 102, right? And you're basically splitting all people based on if they're older than 102 or less than 102, which seems like a really dumb split. But it wouldn't be, because basically probably all the people in above 102, they're going to be in the same class, whatever you're looking at, right? So you might very quickly basically eliminate some data points. So it's not going to be the best split, but it's going to be fast, right? You don't have to do any thinking. You just call your random seed, your random number generator, and pick another one, right? You just choose a value. And then stopping, you don't do any kind of special rules for stopping. You just say, if the size of the leaf node, I forget how we were labeling leaf nodes. Say it's an actual leaf node here. If it's less than 10, you just stop, right? Or 100, depending on your data set size. It's a very simple rules, and it means that this algorithm can be run really quickly, and you can run, hundreds of trees or thousands of trees really quickly. What was the total randomized trees is even more random. Oh yeah, okay, sorry. So extremely randomized trees, you randomly pick the features and you randomly pick a split point, but at least you look at each of those and you pick the best one, right? So you still choose out of maybe the 5 features you picked and quickly compute a score and pick the best one. Totally randomized, you don't even check. You just say, pick a feature, pick a random, split, keep going, right? So it's very fast, but then you can basically use the randomization to create spread. Right, so that's the main difference. They're using randomness, and you're using the whole, since they need more data then, they just use the whole data set every time, right? Because they're basically just doing random samples over and over on the total data set. They just use n for all the trees every time. So that's another difference there. And so this method is also quite good. It's not as good as random forest generally. It's less. I didn't have that anywhere. We'd have to go look it up somewhere, but it's less commonly used than random forest because I think it's a little less robust because it is got so much randomness in it. Sometimes it might go off in the wrong direction. But when you're trying to learn something, build a very fast set of ensembles, and you're going to do something else with it, then it's very useful. Okay, so now we're talking a bit more about boosting because there's this kind of combined algorithm that really takes a lot of the ideas from all of them together and adds one more idea, which is gradients. And it really generalizes this idea of boosting. And this one's a very popular algorithm on scikit-learn. There's this one called, I think it's on scikit-learn, but it's always available to people, XGBoost, which implements this. So it's a very popular one. And it usually does a little bit better than random forest as well. So what does it do? So after people talked about boosting, they realized that boosting is really like this more general algorithm where you're trying to optimize what they're calling the mapping function from the inputs to the outputs, right? And we've got a bunch of weak functions. We've got a bunch of like sub-functions that are very just simple classifiers, and we're trying to combine them together. And what we're trying to do is weight them based on their strength, right? So what they want to do is try to build a gradient approach for this, but what's the gradient of a tree, of a decision tree? How would you do that, right? So if you just remember back to calculus, which is a good thing to start refreshing and getting in your mind. How do I draw this? We've got some function f of x, and it's based on some parameters. So it's going to give us some outputs, and say it's giving us certain performance this way, right? And so the parameters define why it's the way it is, and essentially then to say, oh yeah, we know that it's doing well. Like these were really good, right? Those were a good points, and the classes are correct. And so what we want to do is say, whatever parameters made this possible, you want to make this more likely, right? So we want to come up with a gradient of the parameters, well, gradient of, we want to follow some gradient of this function with respect to those parameters so that, like, conceptually, the points here where it's doing well, we increase the parameters to make those points more likely, right? And the places where it did badly, in some other part, we want to decrease the weights, right? And it's not that we want the function to go up or down, we just want it to be more likely to do the thing it did at these data points. So if you think about what that is what would a very small change to the parameters do? Would it make the data points that you got right more likely to get right, or less likely, right? So in a general, that's what a gradient is, right? When we've got a formula we can define, we can just compute it, we take the derivative and we do that. But with a decision tree, we don't have a function that way, right? So what we're really talking about is saying in a decision tree, what are our parameters? Our parameters are the split points, right, on every tree, right? So when we pick a feature and we say f1 is less than 2.5, that's a parameter, right? That's a particular parameter of this tree, right? And every single split point is another parameter, right? Right? And we can adjust these, right? So say, well, if we made a very small increase, if we added epsilon to this, would it get better or worse, right? If it gets better, then that's a positive gradient. If it gets worse, then it's a negative gradient. So that's all gradients are, right? Infinitesimal changes in the parameter. Would that make the function go higher or lower, right? And so that's essentially what you're trying to do with a decision tree if you're following its gradient. Random forests don't do this, right? Because they're just randomly picking the next data points, and they just hope that the randomness will increase the sample, and they'll learn a robust spread on the data. But AdaBoost and these things are somehow doing that, right? When they come up with a new weak learner, they are essentially optimizing that thing as if they're following the negative gradient, right? So if the gradient means this thing where we say, change that parameter, add an epsilon to it, if it got it right, we're basically going to say, like, we'll find all the places where it got it wrong, right? So places where in the tree where it did badly, let's find those and try to learn a tree that improves on those, right? So we're going to give it another chance to learn, right? So you're basically seeking out the negative gradient of the trees and then giving it a chance to improve. Right, because you're trying to, by training on some data set, you're trying to basically add new parameters that let you fit that. And so you're picking the ones that did badly. You're basically trying to compensate for some places, model one got really bad on data point I because of its parameter 5. Now in tree 2, we're going to make sure it's got data point 5, and we have a new parameter, a whole bunch of parameters that it's learning. Basically, as it goes down the tree, we try to get that up so we get better on it, if that helps. It's implicitly doing the gradient. So the idea of these things is, hey, let's explicitly do that. Let's try to come up with a function, come up with a gradient of these things, and then create trees trained that way. So what we do is we talk about a tree-based ensemble model is really a set of weak learners. So we've got a bunch of trees, right? And I is going to have I trees or weak learners, whatever they're doing. Each of them is trying to come up with a labeling for your classification. If we imagine then after we've learned this one, what would the perfect function? I said there's no perfect functions, but if there was, how would you write it down, right? The next weak learner would be the one that perfectly compensates for the difference, right? So this thing said, what's the probability of the label being Y given the data points X, right? That's essentially what this is doing. But there's going to be an error, right? So if we take essentially the error and say, how badly did that one do? What's the difference between it? We make it a negative. That's going to be what we would need to compensate for, right? And so in the boosting part, we take this error and we add it to the model that we have. How does that work? Oh, we're just adding H, yeah. So H is the filling in the gap in the model from the previous one. So we just add that on top, and then when we optimize this, we're essentially trying to optimize a loss function like this, where we're saying come up with a set of trees that give you these labels, where we are trying to minimize this, right? So we're trying to minimize this this loss. I'm pretty sure it's minimized. Let me say flip it, right, over all the time, and we can set it up as a general formulation that way. So when we get then the final form of it, I think it's the final form, yeah. We can talk about the gradient just being this kind of differences of the, right, this is a definition of our what the gradient of the trees would be. And we know that it's the kind of this filling in the gaps function where we want to take the gradients of all the previous trees and add them together, right? So essentially this is like for all previous trees, what points did it get wrong? Right, so it's exactly the same idea as boosting. We just put it into a kind of formula where we now have a function that describes how many we got wrong over all the data points, and we're trying to maximize that now, right? Because this is being subtracted from it, so we still want to maximize the performance of our current tree while having to deal with this drag of all the ones we've got wrong on the other ones, and we add one to the ensemble that maximizes this. So any function that maximizes this, even if it's not just a normal decision tree, would be boosting in this way, right? And so XGBoost is kind of an implementation of representing decision trees with different kind of, I think they use kernel functions inside to represent all the choices, so rather than just having rules and growing them like a decision tree. they use this and they kind of compute it more directly. But it opened up a whole area of kind of like research into what does boosting mean. This essentially is a gradient search method for searching for better models, which was surprising because when it was defined, it was just this neat idea of like, well, what if the next tree just is trained on the things the previous one did badly on? You know, that simple idea. But it actually showed that it's kind of related to these other gradient descent approaches. Okay, so that's the boosting. So that's the most important part to get through. There's a few more slides. I'll just let people if they have any questions, because there's still, I've got like 7 more slides with the whole of the topic, and I don't know if I can do it in 14 minutes. If there's no questions, I can try. Regardless, I'll continue it after and add the recording myself. Does anybody have any questions on stuff we talked about so far up to here? Looks like not. How many people? Circa 45 people. So, okay, so I'll start this part and we'll see if it's messy. The remainder things are about what if you have streaming data rather than fixed data. Confusing, but no specific questions. This is common. That's fine. Yeah, we'll see how well we use that. I don't know if I want to. If I'm going to ask any kind of testing type questions on gradient boosting with the gradients, I'll give you more details as needed, because what I give you there is a high level view of why it's related to boosting. But you're trying to use that algorithm, beta boost and XG boost. So we'll see how that goes. I mean, if there's more questions, we can talk about them online. Because the last kind of component of this streaming thing is that often we have data arriving, you know, so you're getting data from your like sensor on your car or whatever system you've built, you know, your physical system with sensors and data coming in, or your log files on your computer, or even with data about people, you know, new data comes in every year. So we talked about, I said before, batch versus streaming. Streaming data keeps coming, right? Keeps arriving over time, right? Time is important because it's the data points arrive at a certain moment. There might be a gap between them. All at once, it could be historical data, so there could be time. But time isn't essential because it's all arriving, it's all existed before. Right? So it's not just that time is in the future, but in streaming, more data keeps coming, right? Especially if you have large data, so internet things, you know, data keeps arriving. All the models we talked about so far, if you have new data points, you have to learn again from scratch because you can't just add them. So these two are ways to try to add the ability to basically deal with new data, but keep the tree structure and use everything we've benefited from so far. So a problem with this is if you think about how we've learned trees, what would you do, right? So if you're learning you got some new data points, you've trained one tree, you've trained another, and now new data arrives, right? What do? Do you change? Sorry, that's unreadable. Do you change the old trees, right? Do you just add new ones? When do you delete the old trees or change them? Right? There's all these questions about how would you update your model, because if you want to just insert a new point, that's not easy, right? Because that's like where would be the correct spot for it to go, what was the sampling that happened when you added it. You're basically destroying all the properties of the decision tree if you just try to add a point in after the fact, right? Because at every point when you were building it, you knew all the data and your choice was based on all that data, right? So these two approaches we're talking about here are ways to try and deal with that in a more efficient way. Because obviously you could just delete all your trees and start again when you get new data. But if you're receiving a gigabyte of data a day, that's not feasible, right? The Hoeffding tree doesn't store any data along the way. It tries to build confidence intervals on the data so that every split point, it only splits the data once it's confident enough based on statistical kind of properties. And when new data arrives, they learn new leaves, and those could then become kind of internal nodes. So it allows it to keep growing and to merge and kind of reduce the size of the tree again. But this one kind of can do online learning and scale, specifically good for regression and classification. It uses incremental approaches to building it. What did I have next? Oh, you can't see that. Can you guys see any of the text here? That's weird. Okay, for some reason, the way I inserted the image here, you can't see it. Okay, so what was the idea though? So the question it solves is, how? That is very slow. Okay. Yeah, I'll just show you the algorithm. So the question it solves is trying to say, how do we choose how many examples that we need in order to come up with a split? So if we, where's R? So this is called the Hoeffding bound, just from statistics. And it states, this is what I had on the other slide, but I'll rewrite it here. It states that with probability 1 minus delta, the mean of a variable, what's the variable? We have a variable r. The mean of r is at least greater than or equal to r minus epsilon, right? And epsilon is defined by this formula here. And so it's this relationship where, and r is in the range 0 to r, I guess, or 1 to r. Yeah. Then you have this formula. So we're basically trying to say, can we estimate how good how much data we need for estimating this variable correctly? And C, where's C? Oh, we're not using that. So N is the number of observations, right? So it's the size of the data. But what we're basically saying is how many samples do we need to be sure about this variable? About the average, right? And we could talk about some subset of the data, right? So if you basically want to say that the node in your tree, like you've got a bunch of rows here, that you're just going to use the mean of this as your predictor or as your class. You want to say, well, how big should the size of this be in order for you to be confident on that, right? With probability 1 minus this, and it could be 99% confident or 95% confident. You can set this whatever you want. And so they're using that idea to say, wait until you get enough data points, essentially, to split, right? And so once you've got enough data points in this way so that your confidence between two choices are high enough, then you do a split. So what they do is for every attribute, so every feature, right, we've got F1 and F2 maybe we're considering, the way we've been talking about it before. They compute G, and G is the cost function, I assume. Yes, so there's some kind of cost G that we're computing. And then you do it for two features. You try to pick the two highest, right? And then when you got those two highest, you say, well, if we can get to the point where we can distinguish and say, okay, I now have enough data to be confident that F1 is better, right? And so now I will get rid of that one, and I will split on this feature that I've chosen, and create a new node, right? And so at that point, you decide to split, I guess, on feature L at this point, and you know that you've got enough data to be sufficient in your estimate. So it's trying to basically only build a tree cautiously until it has enough data. And so that means when you receive new data now, you can always just keep adding it to the bottom, because the last leaf you've had is a leaf because it doesn't have enough data to split yet on any of its variables. And once you receive enough new data points, you could split it. So when you receive new data points, I think you add them, you consider adding them to you go down to the tree, right? So when we get a new data point, it's going to still go down through the, right, our new data point x plus 1, it's going to go to like each split point in your tree and end up at some leaf based on the rules that have been decided. But it'll just sit there then and improve the ability of that tree to make a prediction here, right? And eventually, if this node now passes the threshold of epsilon, then it will split it again. So it's a way to just basically don't overcommit. So when we talked about before, like building a very deep decision tree and then pruning back, this would not do pruning, because it never grows more than it actually is allowed to, given the Hoeffding bound. So that is the first way that we could do that for online streaming data. Okay, and that's 10:30, so I'm just going to stop there. The remainder slides are on the second way of streaming, so I'll record that offline and just post it at the end of this with this lecture, and then they'll be up there later today. Well, probably maybe this evening this time because of the busy day I've got. But it's another popular one, and we'll be using modern force. Actually, we'll come back again later for anomaly detection because it's quite a flexible method. But good. So thanks for coming, everyone, and thanks for your questions. And I have my office hour in half an hour. So anyone who does other questions related and wants to talk there, they can. And see you later.